look at bonding in solids. Now, all solids can be classified as one of two things. The first classification is amorphous solids. These are solids where when it solidifies and the particles slip into their spaces so that they can be close to each other, there is no overarching order. They're disorganized. The particles don't get into lattice positions properly, and there's a lot of jumble. Our other type of solids, called crystalline solids, have well-defined structures. Okay, and we call the repeating units unit cells, and they have arrangement. So for example, we can see a crystalline lattice here on the side where my unit cell is a cube, and I have this cube repeating throughout the structure where each of the corners represent a lattice point, and each of the lattice points have repeated specific compounds or ions or molecules. Okay, and so we can see here my crystalline solids have nice organization. My particles are close together, tightly packed and organized. Amorphous solids have significant disorganization. Now, my crystalline solids can be classified or put into 5 different categories, and what category they belong to depends on what's at their lattice sites or in the corners of like that cube. So we have atomic, metallic, ionic, molecular, and covalent network. Now, our simplest type of crystalline solids are atomic solids. They're made up of individual atoms, and the atoms are held into their lattice position by London dispersions. Now, since they're only held in their lattice points or their spaces in the solids by weak London dispersions, they have very low melting points and boiling points. They tend to be non-conductors. They're said to be brittle because if we were to strike them with a hammer, they don't bend or anything. They would actually become a powder, and they're insoluble. Now, good examples of these tend to be our noble gases. Okay, so they're very rare in nature. They have really low melting points and boiling points, and so we don't find very many of these out there. Now, the type of solid that most people are familiar with are ionic solids. In our ionic solids, we know that our lattice spots are occupied by ions. And we can see in our diagram here, for example, the corners are occupied by repeating cation, anion. So we have our chloride ion, then our sodium ion, then our chloride ion, and that pattern repeats regardless of what direction we go out from any specific ion in a straight line. So we have our alternating ions. Now, because they're made up of ions, they're held in their spots by really strong electrostatic attractions because these are full charges, and so it takes a lot of energy to break those attractions. As a result, since it takes a lot of energy to break those attractions, they have really high melting points and boiling points. They tend to be solid at room temperatures. They're hard, and again, they're brittle. Again, if I hit them with a hammer, they'll shatter rather than cleave or give me a nice face. Okay, now, due to the lattice structure, we can explain a lot of their properties based on their structural component. So the fact that they're an ionic bond, which takes lots of energy to break because they're full charges, they are high and have high melting points. Now, they're said to be brittle because we have a directional attraction. So if my chloride ion here is being attracted in a direction, and so that's called a directional attraction, and it's being pulled in that direction and held there. So as a result, if I were to strike this to try and cleave it off, it would take a lot of energy. Okay, and because my ions are held in position in the solid, in their lattice positions, it doesn't allow for them to conduct electricity in their solid state. But in the liquid state, what happens is it frees up the ions so that some of them can move through, and that allows them to conduct electricity. And if we dissolve them in solutions, my ions can then carry charge through the solution. Our next type of solids are molecular solids, and this is where now we start getting full molecules occupying our lattice sites. Okay, now they have crystallized structure like ionic, but their arrangements are much more complex because of the shape and size of the molecules. And the bigger the molecule, the more complex it gets. Because they're held together by our weak intermolecular forces, their melting points and boiling points are lower than that of ionic compounds. They're not very hard because, again, we have weak attractions holding them in their spots. So if I hit them with a hammer, they will deform or they'll shatter easily. And due to the electrons being found in our bonds and not being free to move, they don't conduct electricity. And so ones that we can see or think of at room temperature or in the environment is glucose, or we can look at, for example, solid water. So when water is ice, it exists as a crystal lattice. Our fourth type are metallic solids. And now metallic solids are unique in that we know that metal atoms don't want to keep their valence electrons. And so what happens is that they will lose their valence electrons if I have a piece of elemental metal. So say this was a chunk of iron. But the electrons have nowhere to go. So what they do is they place the electrons in a space between the atoms. Because we know most of the volume of a compound is empty space. So what happened is this atom tossed out its valence electron, and that valence electron now exists in the space between a number of different atoms. And so now what happens is we have what we call a sea of delocalized electrons, because these electrons now that are in the spaces between the atoms don't belong necessarily to one atom, but to all the atoms. And so as a result, we get strong attractions, electrostatic attractions between these ions, but they're not localized. They're not in a specific direction. And so this allows for some of the unique properties, right? So what happens is that if I were to hit this with a hammer, it would be malleable or ductile, because what happens is when I hit this ion here will start to shift. Because I have these electrons that are spaces between, they'll pull them along, and so they'll pull the other ions along with it. And so as a result, this allows metallic solids to be molded into different shapes, and they're also ductile. Okay. Also, because I have these delocalized electrons, if I were to have a heat source down here, this is my candle, I could get these electrons to vibrate, and since they have a low mass, they'll vibrate easily, and then they'll bump into the next one, and this will allow us to propagate our heat through our metallic solid, and as a result, they're really good conductors of electricity. Finally, because I have these delocalized electrons, all I have to do is provide some push and pull force, and I can get them to vibrate or flow through the solid, and making metallic solids good conductors of electricity. Okay, now the properties of metallic solids can be explained a lot due to these delocalized electrons. For example, the fact that they're shiny. My electrons, since they're more mobile and they're in spaces, this allows them to absorb and re-emit energy and be shiny and have lots of different wavelengths that they release. Because we have non-directional bonds, because my electrons are in spaces between and they pull in all directions but in no direction, this allows for my atoms to slide over each other when I'm deforming it. The valence electrons that are in spaces between the atoms can flow easily. Okay, they're hard because I do have lots of electrostatic attractions keeping my cations in lattice positions while the ions are in the spaces between. And so this helps to make sure that my solid has some rigidity. And our final type of solid that we're going to look at are called crystalline solids. Like atomic, my lattice positions are occupied by atoms, but unlike the atomic, rather than weak intermolecular forces holding them in place, we have a covalent bond that holds my atoms in place. And so what happens is that my solid ends up being like one gigantic molecule. And here we have, for example, silicon dioxide. or glass or sand, depending on its arrangement. Okay, now crystalline solids, because covalent bonds rather than electrostatic attractions or intermolecular forces hold my particles in lattice sites, tend to be really hard, because if I want to break the solid, I have to break a covalent bond. Okay, they have the highest melting points that we know of, and they're not conductors of electricity because the electrons are in the bonds. Okay, they do not bend under pressure, so they're brittle. They have really high melting points and boiling points above that of ionic and molecular. Now, carbon is really unique in that because it can form 4 equal bonds, it can form a number of different allotropes or arrangements of crystalline solids. Okay, so our first one is graphite. Graphite is a flat molecule because every carbon atom forms at least one double bond. And so this makes them all have an sp2 hybridization, and they all end up being trigonal planar. So this allows us to make a really long flat molecule with the layers being attracted to each other with weak London dispersion. Now, one of the beauties is because I have these layers, I can have a free electrons flow through it. So if I were to connect this to a power source, my free electrons would flow between these layers. They'd have very little attractions to either of the layers. And so as a result, graphite is one of our only nonmetals that conducts electricity. If my carbon had taken an sp3 hybridization, then what happens is that each carbon will form 4 covalent bonds and will have a tetrahedral shape. And this gives us one of the hardest known substances that we know, a diamond. They don't conduct electricity very well at all because all of my electrons are in bonds, plus I don't have that flat layer for them to flow between. And finally, though, because I have all these different bonds and carbons in the different spots, it will reflect light very well. If I were to take my graphite or chunks of my graphite and make it into hollow tubes, spheres, or ellipsoids, then I would have what are called fullerenes. Now, fullerenes have a variety of different properties. They're used often as lubricants, and this is because they can roll past or move past each other. They're only being held together by, or attracted to each other, by weak intermolecular forces. And this is an example of what we call a buckyball. There's 60 carbon atoms here, and each of these spots are where carbon atoms are, and they're all bonded together. Now, the last and most interesting allotropes of carbon, I think, is a nanotube, because of their shape, it's almost like a sheet of graphite that we've rolled into a tube. They can be really long, and as a result, because we're talking about a covalent bond holding our atoms in their spots, and it's really tiny, if we get a nanotube, or we take a number of these fibers and braid them together, then we get a really high tensile strength structure. They are really good at preventing the hard objects to get through because they're very stiff, and they also do allow electrons to flow through the center as well.